So CS140 is about operating systems. In this class, we used all these things that you will end up building in operating systems, right? Like you build a file system. You built like how you actually, well, you kind of build a little bit of that for this class, but you build like a little lower level file system and more robust and more of the parts for the file system. You don't have to just read and write files. You build the actual file system in 140. You build a threading library or a forking library, a multiprocessing library. And those are the kinds of things that we know how to use now, and then you'll actually do them in 140 where you actually build them and understand what it takes to build a threading library. So it's a good thing you already know how to use these, because then it's much easier to understand how you're going to go and build them. So that's that. And that's about the implementation part of it. Okay. There's also CS143, which is compiler construction. Compilers class, when I was in graduate school, it was one of my favorite classes. I didn't do particularly well, it was hard, but it was a class that I enjoyed a lot because you really get a much more detailed feel for, hey, how does your code end up as machine code? Now you cover that a little bit in 107, but not really the part of like actually doing the translation. Like you see what the beginning and the end are, but compilers is all about translating and doing that. And I think it's a great class. I also happen to think that a lot of employers, when they see that you took a compilers class, actually perk up a little bit and go, oh, well, this person went a little bit outside the normal, because it's not like everybody takes compilers, and they know it's a hard class too. So for what that's worth. I think it's an interesting class, and you might want to take a look at that. If you like the networking things that we did recently, CS144 covers networking. And this is in much more detail than what we did. We just talked about server client and setting up a network and so forth. This networking class digs into more of the details, like how do the bits actually get across the network efficiently. We'll talk a little bit more about that today, just in general terms. But that's what the networking class covers, and it's another good class, especially if you're interested in this sort of stuff. If you do go into security or things, it's probably not a bad idea to take the computer networking class as well, because it's got a lot of the exploits end up exploiting things that might be at the networking layers that you haven't necessarily seen in this class. Okay, so that's the three bigger ones that I think you could go on and take. There's also 144 and 142 and other classes that, 142 is another one that you can take that dig into more systems detail. So there are a lot of systems classes, and again, I do recognize that many of you are like, I'm glad I'm done with systems forever. That's it. But for other people that want to do it, lots of other choices, and feel free to chat with me about that if you want to know some of those other choices. Okay, so here's the principles we want to talk about today. So we want to talk about abstraction. Now, abstraction is what you've been doing, like you've seen abstraction at many, many different layers, and we'll get to the details of what abstraction is all about. We need to talk about how that relates to CS110. Modularity and layering is another one that we're gonna look at. Naming, remember all those things we did with file systems and like name resolution? That's kind of a big principle that you have to deal with. Many of these principles are all about doing things either more efficiently or doing them in such a way that it makes a big system become less gigantic to wrap your head around. That's what a lot of these things are, okay? Or it's a matter of like name resolution is all about, hey, humans are good at names, computers are good at numbers, how do you mix those together so that it works most efficiently for the computer? Virtualization, we'll talk about two different types of virtualization. And then concurrency, which I would argue this class is more about concurrency than probably any other topic. There's more of that kind of filtered in along the way. And then client-server request and response is another one. It's not just networks that deal with client-server request and response. Anytime you have two programs trying to communicate, whether they're on the same computer or across a network or in some other sense, that's where you've got this client-server request response, and understanding how that works is important. Okay. All right. So those are let's jump right in. And of course, hang on. Of course, this isn't working again. There we go. Okay, that maybe. Okay, we'll go without it. Hang on. There we go. All right. There we go. Now that's back. Okay, so abstraction. All right. Abstraction is simply separating what the program is doing from the implementation. Okay, and this is something we've seen in lots of different scenarios. But one example is just a sorting program, right? A sorting program has an interface where you pass a bunch of words in and they come back to you sorted. And that's the interface. Like you may have, you have to put them in an array and you have to say where the beginning and the end of the array is and so forth. That would be the interface. The actual behavior is they get sorted. How that implementation happens is completely up to the program. Now, of course, with sort, you want to do it there are so many different types of sorts, and you don't want to do the one that's going to be O(n), you want to do the one that's going to be O(n) log n or whatever. But in terms of the implementation versus the interface versus the abstracted, this is how it goes, that's the big picture of abstraction. Okay, and we've seen these in many ways. The big challenge a lot of times is to design a clean interface that makes some library you're designing easy to use. Okay, we've actually done a lot of the designing of the interface for you in this class, mainly because it would be really hard to say, hey, it'd be hard to test it, first of all. But second, without a clear interface, you can spend many hours thinking about how to design an interface for something, and you kind of want to do it properly because it is challenging. I would argue that the C++ language, the interfaces are not necessarily as clean as you might hope. For other languages, they tend to be somewhat cleaner. When you do a find in a map and gives you back an iterator and there's a first and a second and all that kind of business that's kind of painful to deal with, all right, that might not be quite as clean. It's there for a reason, but it might not be particularly clean. File systems. So when you use file star and IO streams, and we've used many more IO streams in this class than we did file stars, that's an abstraction that is away from the low level read and write, which is what we saw right at the beginning. And why do we abstract those away? Because again, it's easier. With the read and the write, you have to worry about buffering yourself. You have to worry about, what happens if I try to read 10 bytes and I only get 6 bytes back? Right? These are all abstracted away once you have a good file library like IOStream and file stars and so forth. Okay? Processes. Well, processes, why is that an abstraction? Well, okay, so it's basically, you probably don't know how fork and exec VP work. Right? You'll learn that if you take CS 140 about how those actually work under the hood. But there's an interface there. When you say fork, you know that it creates two processes, and you don't really care how that happens, but you know that now you've got two processes, and you've got a child and a parent, and so forth. And there's lots of other things happening to keep track of the child, to be able to wait PID, and so forth. That's all an abstraction. Signals is another one. If you took CS 107E, you definitely did interrupts, which are basically signals, and you know a little bit more about how those work. But the idea that you've got the kernel keeping track of a bunch of things that you don't necessarily you want the kernel to keep track of it, but you don't really know how it's doing that. You just know that when something happens, the kernel goes and tells your program, calls a handler function or whatever. That's basically a signal. So that's abstracted away too. The abstraction there is, okay, I've got a signal handler that's going to get called when something happens, and how does that actually, the mechanics of that, it's all abstracted away from you. Okay, if you go take operating systems, you'll learn more about how that happens, or maybe some EE classes too, where you deal with that. Threads, same sort of thing. Remember, threads and processes are similar. Threads are kind of lightweight processes, but it's the same idea. You've got these threads. How does it work? Well, we don't really know. We know how to use them, and we know how to use them efficiently. That's that. HTTP. So this is what your last assignment, the proxy, was all about. And HTTP defines how things get sent across the network and the various messages that it gets. And that's abstracted away again. You generally, with your web browser, don't need to worry about get and post and that sort of thing. Okay? All right, so that's abstraction. Okay? Modularity and layering. So when you talk about modularity, we're basically saying subdivide a larger system into a bunch of smaller systems. This is decomposition. We've been doing this since day one of 106A or 106B, and it's important. One of my favorite examples of a large system that's complex is, believe it or not, a Xerox machine. So how many people have used, like everybody's used a Xerox machine, a copy machine before, right? Well, we have some in the CS department that are able to copy like hundreds of exams for like CS 106B and CS 106A and whatever. And these machines are super duper complicated, right? If you go and you think about what has to happen to make copies of pages in a certain form, it's pretty intense. So for instance, okay, right? Xerox copy machines are supposed to like copy paper. Like, that's the big picture, right? Paper, there we go. Supposed to copy paper, and that's what they do. But what else do they do? Well, they handle double-sided, right? What does that actually mean, right? It means you either have to have a way to write on both sides of the paper, which is not really what happens generally, because that would be kind of weird, especially because gravity might come into play a little bit. But you also have to, or you have to flip the paper over, and that's a mechanical engineering challenge, right? So you've got that in there. These things sometimes staple, right? Stapling involves getting the paper in exactly the right place. I mean, oh, by the way, it also has collating, right? Which is where you have to have like all the different stacks of the right thing. How does collating work? Well, if you have a 20-page exam, like the CS 110 exam, might not be 20 pages, but let's say you have a 20-page exam, right? Well, there better be enough memory in your system to hold all 20 pages, or some of the older machines had to refeed the paper in every time it wanted to do a 20-page thing because it didn't have enough memory for that. So that's a big thing. So there's memory in there. Let's see. It's got networking associated with it. If you can, like, I can send a print job to the Xerox copier. I can do that. What else does it have? There's also the whole physical layer that's or the actual physics that goes into it. Like, do you guys know how copiers actually work? Like physically how they do it? Okay, so there's a piece of paper that's blank. And, oh, by the way, there's also lasers, right? There's a laser that's inside your copy machine, right? And that's kind of cool. And it actually, the laser charges up your paper. Let's say it's a negative charge. I don't know which direction. It charges up the various dots on your paper where there's going to be the toner. And then the rest of the copy machine takes the toner, which is that powdery black horrible stuff, and it charges it the opposite charge. And then it dumps a bunch of toner on the paper, believe it or not, and then it where the charges are there, it sticks to it, and then it sweeps off the excess. All right. Actually, I think first it fuses it, and then it sweeps it off, or maybe the other way around. But it basically does that, and then there's a heating business in there, and that's why it always comes out warm. And my point is that these things are so complex that no one person, in fact, no 10 people, know enough about the entire machine to be able to like fix it or do it all by themselves, or even understand it to be able to tell you all about all the details, right? There's physicists, there's engineers, oh, by the way, there's all the software. You know how many different menus are on that thing, right? There's so much software on there, right? That like has to do it all and get everything right, and then there's mechanical engineering that goes into it. I mean, there's so many people that work on that. It has to be subdivided. It's just way too big. You would never have one person creating a Xerox machine by herself, right? It's just impossible because one person can't do that. So that's that. Another good example is the phone in your pocket, right? If you took 107E with me, you remember we talked about like all the different sensors that are on your phone, right? There's probably 15 different sensors on here. Did you know there's 4 radios in your phone? There's 4 different radios in your phone. There's the one for the regular like phone calls, which isn't even the regular thing you do anymore. Like that's like the least used thing you use your phone for anymore. There's the Wi-Fi one. There's a Bluetooth one. There's let's see. There's another one that communicates with the with when you do Apple Pay or whatever. So I mean, there's all sorts of radios in your phone. There's cameras. There's at least 3 different cameras. There's a camera on the front. There's a camera on the back. There's a camera underneath the fingerprint thing. If you've got that, that's how that works, right? Some ones have cameras built into the screen now. I mean, that's not even to mention there's a temperature sensor, there's a drop sensor, there's an accelerometer, there's a gyroscope, right? Who understands all those things? Like nobody understands every little bit about that, right? There's specific engineers whose job is to do the gyroscope part of the iPhone, and that's how it works, right? But it's all about subdivision of this larger system. So you have to understand how that works if you're going to be building bigger projects. Right? Now, at the same time, you might go to Apple and work on the iPhone and be like, "Oh, I'm the person who's doing the fingerprint sensor and whatever," and you're not the only one. But you might feel like you're doing a very small part of a much bigger thing, and you have to keep that in mind. That there is a bigger project here that ends up being there. But that's what you have to understand. This class hopefully gave you assignments that were somewhat robust, and there were lots of moving parts, and that's why there's 20 different header files and whatever, because you have to kind of try to understand that. And we don't make it too complex that you can't, as one person, understand it, but we need to push that limit to say, oh, we better break these into various subsystems, otherwise it's not going to happen. Okay? File systems. Here's a good example of layering here, where you've got lots of, not necessarily modularity, but you've got layering, which is putting one layer on top of the other so that you break it down into its various components. Remember for your assignment 2, there was this like symbolic link. Well, we didn't have to do symbolic links, but you could have. We had to read about those and learn about those. There's an absolute path name, which is like /user, /class, etc. There's a path name layer, which actually takes the, which can take things like // whatever, and then layers it onto an actual thing there. There's the file name layer, which actually does the files for human reading. That's where you've got that layer. Then you've got the inode layer. Remember, each file has an inode. Why? Because computers are better at numbers than trying to figure out a whole like path. It's much slower to do that. And then there's the file layer, which is where like the bits themselves, what they consist of on the drive, like your actual files. And then there's the block layer, which is like where on the disk they are. All of those different layers come together to make a file system. And you have to at least understand parts of those layers, or at least how your layer, if you're working on one particular layer, interacts with the next layer down. Hopefully not more than a couple layers down, but that's you have to understand that when you're doing that. Okay, all right. What else do we have on modularity and layering? So this is one that you don't really go into this much detail. Maybe you probably do in a compiler's class, but I'm about to show you some layering that happens in G++. You know how you have your program and it turns it into a binary? Well, there's lots of steps in there. It's not just like it just goes through once and turns everything straight into binary. Okay, there's lots of different parts, and we're going to see some of those parts in particular so that you can actually see what the compiler actually has to do. First one we're going to look at is the preprocessor. So the preprocessor is one of the ones that all the pound includes or pound defines, or as you youngsters call them, hash includes or hash defines. The preprocessor is what takes those and manipulates them and changes those into something else that the next layer down can do. Let me show you what I'm talking about. Okay, what we're going to do is we're going to go over and we're going to do a little program called hello.cc, and it's going to be very simple. It's going to be like day 1 of 106B here. IO stream, okay, using namespace std, okay, and then let's do a pound define, because we've got 2 pound things here, the include and then the pound define. I'll talk this k range start 100, okay, and then int main, int argc, int char star argv, okay, and then let's do this. For int I equals k range start, I is less than k range start plus 10, I plus plus. Okay, and then in here we'll do cout hello world, and then we'll actually do the I as well, like that, and that's it. Okay, so pretty straightforward program. Anybody see any bugs? Okay, what I'm going to do, I'm actually not doing this on Myth. I'm actually doing this on my computer because I'm going to use a slightly different compiler. I'm going to use the compiler called Clang, which allows you to break out some of the details here that G++ for some reason doesn't let you. You might be able to. I couldn't figure out the way to do it. But in Clang, you'll see it. So if we do the following, clang-e hello.cc. Okay, actually, let's do this first. Clang hello.cc -o hello. Okay, make sure it works. And if everything works right, oh no, maybe I need to do Clang++. Hang on. There we go, that worked. So I guess Clang++ will work. So if we do hello in this case, right, it will do that, and that makes sense. Okay, that's what our program is. If we do, let's try Clang this time. Clang-e hello.cpp. This is saying run the preprocessor. That's the one that deals with the pound includes and pound defines. Okay, and why is this not working? Oh, it's CC, that's why. There we go, there we go. Okay, did you see that? See all that stuff that went by? Here's what it's actually doing. Okay, so what it's doing is it's taking a bunch of the, well, first of all, it's taking the pound include and including it. And guess what? That pound include header file probably also has includes, and it needs to include all those. And it just basically creates one more file that is all the stuff that you're about to process in one file. Okay, and it does that. In fact, let's see how big just the preprocessor creates. Word count, 41,000 lines comes out of our one hello world program just from taking that preprocessor in there. But let's take a look at without hello.cc. Let's take a look at it without the cout in there and without the, because you don't, let's just look at what happens to the k range start in here. Okay. All right, if we do the same thing again, at only 18 lines, so that's much better. Okay, so here's what it did. This stuff at the top here is just, it's other information that's going to be used by other stages of the compiler, so file amounts and so forth. And notice what it did with our pound define. It took that k range start and replaced it with the 100, and it replaced the 100 here, and that's all it did. Took whatever you define and just went through the entire program, found where it was defined, used, and then replaced it. That's all it does. It doesn't do anything else in this case. It might actually do a little bit of replacing of variables if you set it up that way, but that's it. So that's what the preprocessor does, and that's the first stage. Okay? The next stage is called the Lexer, and the Lexer is what takes the translation of a stream of tokens, right? It takes all those, the program and turns it into individual tokens of what's happening in your program. Okay, let me show you what I mean by that. Okay, if we do the, let's go back and make it the original one again. So we'll do that, and we'll put this back just so we can see the original again. Okay, and let's do this. In this case, we have to do clang-xclang-dump tokens and hello.cc. What it actually does is it actually puts the output, for some reason, in standard error. So I'm going to actually pipe or redirect standard error to standard out, which you may or may not know that you can do, but you can. And this, you just use the 2 angle bracket &1. But it does that. And then we're going to look at it. And here's what comes out. Okay, so what has it done here? It has taken a type def, called type def in this case, and there's a type def in there that it actually created. And let's see, there was a char 16t in there that it created, and more type defs. You know what, this is actually, now that I look at it, this is just the, this is all the included file in here, so let's get rid of that again. And you'll see what it looks like with just the part of the program that we have, and you'll see how it actually, let's see, there we go. All right, let's try this again. There we go. Okay, here we go. So here's what it did. It had to find our int. Remember we just had that for loop in there. What it did was it said it has an int here, and it found main, and this is for the int return value for main. And then it found main in here, and it says that's an identifier, main. And the program is going to be the compiler is going to be looking for main. Oh, guess what? It found a left parenthesis. This is the main. Remember, it's like int main parenthesis, right? Well, that's the parenthesis there, and it calls it a left paren, and it's taking it down to that level where it finds each individual token and does that. There's another int in there, there's an argc variable, there's a comma, right? You probably never thought about, oh, we have to deal with all this. If you're writing a programming language, that comma means something, right? That parenthesis means something. Well, it's just another token that gets taken into the thing. We have some brackets in here for char star argv. Let's see what else we have. Let's see if I can get some more there. Let's see, can we find any of the ones that we had? Here's our identifier I that we put in there, right? It has that in there. There's the plus plus. It actually calls it plus plus. right? And it does it so, this is, part of this, by the way, is so that it can do much more translation than some other compilers. It like breaks it down to this level. But it does need to tokenize it, and that's a layering sort of idea, okay? Then, after we go through the Lexer, which gets all those tokens, then it goes into a more interesting part. So far, this is like, oh, that's just translation. That's not too bad. Then it goes into this one called a parser. And a parser is now looking at syntax, okay? And the parser says, oh, let's group these tokens into syntactically valid constructs, okay? So let's see what we do that. This one is also xclang again. This one, it's AST dump like this. AST dump like that. And now it actually is creating a little tree. We call this an abstract syntax tree that actually has all different parts in there. So let's see if we can find something in here that we've done here. Here we go. So remember we have a for statement in there. Well, the for statement is made up of a compound statement, right? A compound statement up here, let's say, okay? And then you've got a for statement, and then a declarative statement in there, which is like the individual parts of the for loop. Let's see, we've got an int. Oh, there's our 100 for the integer that we had, the constant in there. We've got to have a bool because there's a less than calculation in there. So there's a Boolean value that's going on when we're doing that. We've got another int in there for probably the next part of the for loop. Let's see, we've got the 10 in there for the plus. We're going to have a plus in there, which is our binary operator. So all these things, somebody had to think about, how does the C++ language turn into this abstract syntax tree? And when you build computer languages, you don't necessarily, well, you have to think about this on some level. But there are tools that do a lot of this for you as well. And then you can see there's the postfix again, and plus plus and so forth. So that's how you end up with the parsing part of it, which is actually a very interesting part of computer programming language design. Okay, let's see. There are a couple more parts here. There is the Semantic Analyzer. Okay, and the Semantic Analyzer part is right here. That's the part that takes all those syntactically valid constructs and says, does this actually work in C++? Like so far it's taken it and saying, okay, this maps to this like little part of the tree, and then it goes, oh, now I'm going to see if this works with the type system, and if you can, so you're going to have to eventually put out assembly code. So it needs to do that. Unfortunately, Clang doesn't show you the Semantic Analyzer part, so that's that. But finally, there's a code gen part, which is what you may have, or what you would have thought about in CS107, which hopefully isn't bringing back bad memories. But if we do the same sort of thing now, instead of AST dump, now we just want to do, I think it's -s actually. So if we do, let's not do the xclang anymore, clang, I'll do plus plus again, plus plus, hello, we'll do a -s, hello.cc, let's see if, there we go, and then, yeah, there we go, hello.s, well, here's all your assembly language that came out. Right? And that's the final part is generating the assembly language. What's cool about Clang is it actually tries to comment its code. It's kind of neat. You know, it's nice of them to do this. This interlude, it talks about the inner loops and so forth. Another interesting thing about this, so let's look up, let's do this. Let me recompile this using the big one. By the way, let's see, how long is this? This one is 923 bytes. If we put back in, we put back in the two parts here just to actually do the printing. Let's see. There we go. And now it is how big? It's now 49 kilobytes, right? So it changes a little bit when you have to all of a sudden print something out, right? There's a lot more going on here. But let's look for the cout function, for instance. There's our cout function. Now, notice something interesting about it. It's not a very good color. Notice something interesting about the cout function. It's got all this garbage around it, like underscore, ZN, ST3. You didn't see that when you saw your functions in C code for an assembly or whatever. The reason is because C++ allows you to overload functions. right? So you can't have just one C out. You could have 10 C outs that all have different parameters and things. So what it needs to do is it needs to do what's called name mangling. And it actually mangles the name and keeps track of it, of course, but it mangles the name so that if you had 2 different or 10 different C outs, it would know which one to call, and you can't do that in C. It's one of the reasons we do 107 in C instead of C++, because it can't do that. It doesn't do this, and it's much easier to read this sort of code. So that's one thing you can look at in there. So there you go. That's the different parts of the compiler. Okay, so you have all these different parts that happen, and it's all about layering, and it does one thing at a time and does multiple passes across the code that you can then use. Okay, or then uses to actually build your assembly code. It's kind of amazing to me that compilers go as fast as they do. I mean, your computer is already fast, but making them go fast enough to compile your code just like that, when you think about all these different things that have to happen. Oh, and by the way, that didn't even talk about compiling with -03 in there, or some other one, right? If we had taken out the cout statement again and did 03, you would have had like a 20-byte file, because it would have optimized everything out, because nothing actually got printed. So all that optimization takes more time and so forth. And if you take a compiler's class, you'll learn this, that compiling time is not really that important. It's your runtime that becomes more important. So it does take more time to compile something. That's actually okay. Now, you do have to worry about programmer efficiency, and you can't take days to compile things, or hours like it used to. But it doesn't matter if it takes a little longer to compile, as long as it optimizes to make your program actually faster. You only have to compile once. You may run it a million times. So that's how that works. Okay. What else are we going to talk about? Computer networks. So that's layers. Right? There's tons of layers in your computer networks here. Okay? There's the TCP/IP layer, right? Which is the data of how packets get transmitted back and forth. I talked about this the other day, where it's the TCP layer that says, oh, here's your packets in a particular, or in order, like 0 through 100 packets. And it's that layer that on the other side gets the packet and then says, oh, I've got the packet, I've got packet 7, I'm going to send an acknowledgement for packet 7 back to the original calling, the computer that sent me the packet, and so forth. So that's what the TCP layer does. Okay, but there's all these other layers in here as well. There's the application layer, which is where you're writing your application when using these sorts of things. There's the transport layer, which is where the TCP happens. There's the network layer. The network layer is the part where it says, okay, I want to send my packet to a particular computer, but first it needs to go through the next closest router, like the one that's in the ceiling or whatever for your Wi-Fi packets and so forth. Okay. In fact, let's take a look at how you might figure that out, or how you might do a little analysis there. There is a command which is traceroute. Did I show you traceroute before? I didn't in some other classes. Traceroute. If you took 106B with me, you would have seen this. Traceroute is a way to find out all the different paths that the path, one particular path, let's say, that your packets might go through. So I happen to find a engineering University of New South Wales in Australia, edu.au. If we try to trace the packets here, oh no, it's not going to let me. This happened earlier when I tried this on my desk. Sometimes it fails and it won't let you. So I think, see, there we go. I did do it earlier just in case this would happen. So let's pretend that didn't fail. You have to be prepared. So what it did was it actually, if it worked, it would have shown you all these different routes here, which basically says my computer, which is 10.34.160.2, needs to go to, or I guess that might be the router, actually. My computer might first go to the router. And then it goes to something at SUNET, which is still on Stanford. Then it goes to another 171, which is still at Stanford. Then it goes to another SUNET, which is still at Stanford. It takes 4 hops just to get off the Stanford campus if it's trying to go to Australia. Why? Because we have a lot of computers on here and a lot of different ways. You need to go through a lot of steps just to get out of your local network. Okay, part of that is because we don't have enough IP addresses to go around. Then it goes to this thing called CNIC, which is I believe that's something to do with the universities in the Bay Area and kind of the Pacific Northwest, Pacific somewhere. Then it has to get to Australia, so it goes to this place called Pacific Wave, which is a ISP or a router that basically sends things across the ocean. And you can actually see, if you go, let's see if I still have this up here. There we go. You can actually see all the different submarine cables that are around. You might ask yourself, wait, why don't I always thought these like signals to go to Australia would go through like satellites and things, right? Sometimes they do, but it turns out it's much faster to go through the underwater, believe it or not. Any ideas why? Actually, the radio waves are actually faster in the air than in underwater cables. Any ideas why? How far away are geosynchronous satellites? Anybody have any idea? How many? 22,000 miles away. It takes about 1/8 of a second for light to go 22,000 miles up to the satellite, and then another 1/8 of a second to go 22,000 miles back. That's 1/4 of a second delay. And if you've ever called anybody, so let's say in Australia, and you did get on a satellite connection, there's a big delay there because it takes that much time to do it. Versus the 8,000 miles one direction to get from like here to Australia, or 10,000 miles, it's much less time over the network. But anyway, you can actually play around with this map and zoom in and zoom out and whatever, and see all the different various connectors. Underwater cables are kind of cool in that they spool them out with these giant spools, and they just have a boat driving along, spooling out the cable. And every so often, then they have to splice the cables together when they run out of a spool. And they do that for thousands of miles across the ocean. It just sinks to the bottom. Sharks really like these cables too. They can actually sense the electricity kind of going through them, so they bite them a lot. They break a lot, so they have to deal with that too, and they make them thick enough, whatever. Chase.
How do they retrieve the cables?
How do they retrieve the cables? Yeah, when a shark bites it and splits it, they have a big hook that they know where it is, basically, with GPS and so forth. And they have a hook that they go along until they hook it, and then they reel it up. So yeah, I don't know what it does to all the wildlife in the bottom, but it's yeah.
What's the different colors?
I think the different colors just mean I don't know what the different colors mean. Good question. Might be different companies that run them. It might be well, they are specific cables, but there's a bunch of gray ones here, and I don't know what the gray ones. I don't know what they are. Yeah. The military? I don't know. Yeah, maybe that's it. I don't know. But anyway, there are lots of cables around the world that because there are lots of people communicating, and that's the way it goes. But anyway, that's another layer, right? That you need to go through the network layer that sends these, and that would be the physical layer, by the way. That's another layer that these things go through. Okay. So another layers that we talk about. I guess we don't put the layer. There's the link layer, which basically is. Let's see, the link layer, I think, is between the network layer is between the computer and the next router. The link layer might be either internal to the router or not exactly sure. I'll have to look that one up. But you can look up more different types of layers there. We generally use the application layer, right? When you do socket and bind and all those things, that's generally the application layer that we need to deal with. Take a networking class, you go a couple more layers down. Okay, 144 is what you might want to do that. Okay, what else? The naming and name resolution. Here's another one. So we've already seen some of this with our file system examples. We've said, we've talked about absolute and relative path names and whether or not humans like Google.com and computers like 74, etc. Okay, we've done that. URLs are also human readable. Remember, URLs can map to IP addresses with a file path name as well. Okay, so there's that in there. File descriptors. A file descriptor was just a number, right? But that number goes to a file descriptor table, which has all the other details, and that's that. So lots of different places where you can see naming and name resolution that you'll see as you build bigger programs. Let's see, caching. So here's a topic that I was actually a little surprised this topic wasn't covered in as much detail in 110. I believe it's covered in more detail, and correct me if I'm wrong, but people have taken EE 180. Has anybody taken EE 180? nobody has. I think EE180 covers caching in more detail. But I wanted to spend 10 or so minutes talking about caching. This is what I would have covered if I was designing this course from scratch. I would probably cover this in a little more detail. Here's how memory works on your computer. You have main memory in your computer, and it's a lot, right? It's normally like 8 gigabytes, or sometimes there's 16 or 32 gigabytes of main memory. It's memory that is random access and goes away when your computer dies. There's also, by the way, the hard drive or SSD. That doesn't go away. It's just super slow. It's also much, much bigger, a terabyte or many, many hundreds of gigabytes. But there's main memory, which is the RAM. Your computer also has these various caches. So you might have a cache called an L2 cache. You might have an L4 cache, an L3 cache, an L2 cache, and then an L1 cache, let's say. And each one of these caches is smaller and smaller in amount of memory, but also faster than the previous level. Okay? What makes an L2 cache faster than main memory? Number one, it's generally built right on the chip itself, like on the processor chip itself. Okay, so it's close, and the wires are really close to each other, and it doesn't need to go to some other bus and so forth. L1 is another one that's maybe built with also basically on the chip, and also uses a different technology maybe to make it even smaller or even faster, but it takes up more space maybe or something like that. And then finally you have the register file, which you've done in 107 or 107E, which is super, super fast memory, but you have like 32 registers or something like that. Right? And in fact, there's more on different processors, but a very small amount. You might have something like, I don't know, 8 kilobytes or maybe 128 kilobytes of N1 and then 256 kilobytes of L2, etc. What these are there for is when you're requesting data, you generally request data often, the same data sometimes, many times. If you have a variable I that you're looping over, right? If you're looping over it 100,000 times, you're going to access that variable 100,000 times. So you might want to keep it in a register or keep it in an L1 cache, somewhere where it's going to be really fast to access, because you don't want to have to go to main memory and go look for it. Here's the difference between like main memory and the registers. There's a good analogy about this. Main memory, let's do it this way. Let's say that registers is like if I had this pen, and let's say this is a register. I have the pen sitting here and I want to write something. Going to a register, I have to pick up the pen and I have to write something, and then I have to put the pen down. Okay? Going to the L1 cache, it might be like the pen is way over here on the table. And in order to go to the L1 cache, I have to go over and I have to get the pen, and I have to come back and I have to write it down. That's how much slower the L1 is. L2 might be the pen isn't on the table, it's over in Gates or something. I have to go back to my office and I have to get the pen and I have to come back. That's how much slower it is for L2. Main memory would be like, let's see, the data is in San Francisco and I have to walk there to get the data, right? So that's how much slower it is. It's a million times slower, like in some cases, right? So you have to go, walk to San Francisco, come back with a pen. That's it. Drive is like the data is in New York City and I have to walk to New York City and go get it, right? Like that's how much slower it is to get something off your hard drive or your solid state disk than it is from the register. So you'd think it's pretty important then to keep things as low in memory as possible if you're using them often, okay? What I wanted to do is I wanted to show you a little example of how a cache actually works. Some of the numbers that might go into using a cache. You do not need to know any of this for the final exam or whatever. I just want to show it to you just to give you a feel for how caches actually, what they have to do to keep the data. Okay? What we're going to do is we're going to look at a thing called a direct mapped cache. Okay? And here's what this is. Let's say that you had 32 kilobytes of memory, okay? And in order to do 32 kilobytes of memory, we would need to have 5 bits of information, okay? 1 bit per byte, as it turns out, or well, 1 bit for 2 to the 5th number of kilobytes or whatever, right? So you need 5 bits of information there. Okay, like 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, all the way down to 1, 1, 1, 1, 1. Let's say that was your main memory. Okay? what we're going to want to do is we're going to want to have a smaller amount of memory. Okay, so sorry, not 32 kilobytes, 32 addresses. That would make more sense. So you can do it in five bits here. Okay, 32 addresses. But let's say that we have a cache that only has space for 8 of those memory sections. Okay, let's do it like this. Let's say that you had 8 bits in here. 1, 2, 3, 4, 5, 6, 7. Is that 1, 2, 3, 4, 5, 6, 7? Any more? 8. Okay. How many bits do I need to represent 8 different locations? How many? 3. You need 3 bits, right? So we're going to have this thing called a tag, or an index rather. An index, which is going to be 0, 0, 0, 0, 0, 1, and, oh, actually, sorry, I'm going to do this. Oops, oh no, can I do it? Hang on. There we go. Okay, hold on. It didn't, hang on. We're going to have I put it in the wrong place here. We're going to have the index here, or maybe I did put it in the right place. Anyways, the index here, and the index is the part that tells us, yeah, so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. There's our 8 locations that we're going to be able to store some of those 32 addresses in, okay? 0 is going to map to 0, 1 is going to map to 1, 2 is going to map to 0, 1, 0, etc. Where do you think 7 is going to go to 1, 1, 1? Where do you think 8 is going to go? Back to 0, right? We're going to use some modulus here to actually do the thing. We're basically going to store them based on the upper 3 bits of their address. Okay? And so, I'm sorry, it's actually, this is where I got confused. It's the lower 3 bits of their address that we're going to do. So basically, the 0, 0, 0 is going to go in 0, 0, 0, 0, 0, 1 is going to go there, etc. Okay? And remember, what we're trying to do is we're trying to say, every time you ask for some memory, it's going to first look in this very fast cache, and if it finds it, it's going to return it faster than if it had to look it up in main memory. Okay? At the beginning, nothing is in your cache. Okay? We are going to try to look up the following 10 different values. Okay? We are going to look up 10110, then we're going to look up 11010, and then 10110, and then 11010, and I've got the rest in here too. We're going to look up 10000, 00011, 1, 2, 3, 4, 5, 6. We need 4 more. We're going to be 10000, 10010, 10000. What did you do in class today? I listened to Chris list off a bunch of binary numbers. And then 11010. Okay, we're going to look up all those numbers, look up all those addresses. And if you look it up and it's not in the cache, it's called a cache miss, and that's expensive. We want to get cache hits, which means that it's in the thing. Because this is direct addressed, it actually turns out that we can't keep the values in there very long. There's other kinds of caching which allows you to keep the data in there longer. But we're just going to see this example and see how it works. Here's what you do. You go to, let's say we look up 10110. We look at the 110, and we go over here and we find the index, and this is called the tag, by the way. And we look it up and we say, is 110 filled or not? Well, 110 is not filled. So what we do is we say, first of all, we say that that's a cache miss. And we put the 10, well, we put the, let's do this. We put the memory for 10 in here. We'll put 1 for 10110, the memory for that in there. And then we're going to tag it with the 10 to differentiate it from the other things that might fit in that bucket. Okay? So we looked up 10110. We looked at the 110. I did it in the wrong one, didn't I? You guys got to catch me on this. We did it in the wrong one. 110, and we looked at 10, and then we're getting the memory from 10110. Okay, that's what we're putting. We're putting that memory there. So when next time we look that up, we will get it quickly. So let's look at the next one. 11010. We look at 010, and we go over to 010. Is it there? No. So it's another miss. And we do the same thing here. We've got 1, 1, and then we have the memory from that location. Doesn't matter what that is right now. Okay, and then now it's in the cache. Let's look up 10110 again. We go to 110. It's there. Is 10 the tag? It's there. We quickly return this value. That is a cache hit, and that's a good thing. And that means that we've got that value in there. And you can think that if we're going to access that number many times, well, we'll always find it in the cache until it gets replaced by something else. Let's look at the next one. 11010. We look at the 010, 01011. It is also in there already, so that's another hit. Okay, let's look at 10000. Not there, so we put the 10 there, and we have the memory from that location. That's a miss. 00011. 00011, it's a miss. And we'll get to one that's interesting in a second. 1, the memory there. And then 10000. Okay, 100. Oh, we already seen that one too? Yes, we did. That's a hit. Okay, and then 10010. Okay, we go to 010. Aha, 010. It's 11, but we're looking for 10. We now evict what's there in the cache. That's what they call it, cache eviction. We send it out. We put the 10 there, and we replace it with the memory from 10010. Okay, and then let's do this one, and that was a miss because it wasn't what we were looking for. 10000 is a 10000. It's a hit again. And then the final one, 11010. Well, we've looked at this one a whole bunch of times, but now 11010, we go back to 010. Oh, we have to kick this one out again, and that's another miss. And now we put this one back in there. This method is great because it's fast to look up. It's not great if you happen to get two pieces of data that are both mapped to the same bucket at the same time. But anyway, that's how you do this mapping. A lot of times this is supported with hardware, so these things can be done in parallel. A lot of this can be done in parallel. And it's also, there are ways to do it so that the values can go in any position in the cache, and you have to determine whether or not to kick something out of the cache based on how long it's been there. If it's been there most recently, then you don't kick it out. If it's been there a long time, you kick it out, or whatever. And you have to go through that. So I just wanted to show you that's a little of the math that you might have to go through if you take EE 180 and you work on how do caches actually do their thing. Okay, so that's that one. Okay, questions on caching? Yeah, Oscar.
When you ask for a malloc, is that main memory? What part of memory is that?
Very good question. The question was if you do malloc, where does it come from? Totally depends. Generally, if the computer hasn't used that memory location recently, then it will have to go to main memory to request it. If it has been used for maybe from other programs or whatever, but it's not being used by another program now, it might still be in the cache. But if you do malloc, it might get a bunch out of in fact, it won't actually need to read any in from malloc. It just says, hey, here's your locations. First time you try to read from a location, it will populate it in the cache. The next time it will be there, hopefully, and it'll be much faster. And by the way, those 4 levels of caches or whatever, it keeps bumping it down, 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 down as farther, the more you do. So your data will be in all the upper level caches, but it looks in the lowest one first. Doesn't find it, looks in the next one, doesn't find it, and then eventually gets up to where it finds it. Yeah, good question. Any other questions on this? Okay, let's look at some more, let's see, whiteboard, there we go. Okay, so that was caching. Virtualization, yeah, question.
Yeah, actually just thought of this. So stuff from your stack, does it ever move to your cache, or is it just kind of forever in that?
Yeah, so the question is your stack moved to your cache? Sure it is, right? I mean, the cache is separate from your program itself, right? The cache is based on how often you use that data. And if you use it, it gets looked for in the cache. If it's not there, it gets put in the cache once it finds it. And so, again, there's various strategies for doing this. What you're trying to do is you're trying to get about, if you can, 90% cache hits in your lower level caches so that it's very fast. And this really does speed things up, I mean, significantly. Yeah?
So your virtual memory for a particular program has potentially addresses that are in the L1 cache, L2 cache, hard drive, and they're all being
Yeah, so yeah, the question is, are these being virtually mapped in here? And they are all being virtually mapped in. The addresses that are stored, or the memory addresses that are stored in the caches are actually physical addresses. So a particular program will have a physical address. Now, another question that might come up is, wait, what happens when you do multiprocessing and you shift off the processor? Do all the caches remain or do they go away? Generally, they get cleared for a different process. They might get saved and repopulated, but generally, I think they just get cleared. So every time you do a process switch, your caches get cleared, which slows things down significantly too. You talk about caches as being hot or cold. A cold cache doesn't have any memory in it yet. A hot cache has all the memory there. It's really fast to access. What other kinds of caches, by the way, do we have? You did a web browser cache, or you did a web cache, web proxy cache. DNS caches is whenever you're trying to request Google's address. Trust me, your local cache has Google's address because people use it all the time, so it doesn't need to go find it. And then let's see, there's another one called memcached, which is, I don't know much about that, but it's for web content that keeps the web content cached in a slightly different way. So there's lots of different places where caching becomes important, and it does significantly speed things up. Okay. All right, what else can we do? Virtualization. So I've mentioned virtualization a few times. You've seen it in labs and so forth as well. Virtualization, there are two types. One is an abstraction that makes many resources look like one. Okay? Let me give you an example. There's a hard drive system called RAID, R-A-I-D, and it basically says, let's say that you have a computer and it has many hard drives. Why would you have that? A couple of reasons. You might have 4 hard drives associated with one particular server. One reason is that you can keep file 1 here, part of file 1 here, and another part of file 1 here, and another part of file 1 here, and another part of file 1 here, and maybe throughout those 4 disks it's duplicated in such a way that if this entire disk dies, then you can recoup file 1 just with the other 3 disks. Okay, it's very good for redundancy reasons. Okay, but let's say that another reason you could do it is if you kept file 1 here and file 1 here. Remember, reading from a hard drive is slow. What if you can do it in parallel and have one process reading from this drive and the other process reading from this drive to get part of the same file? You can actually do it almost twice as fast because both disks will be running in parallel to give you your data. So it's both for robustness and for safety, as far as robustness and for speed, rather, so that you can get your data faster. But by the way, your file system, when you access a file, it has no idea that there's 4 disks here. It looks like just you make one request and it gives you the data back. Internally to the RAID system, it does all these special, there's 4 disks and I have to do that. That's a virtualization. 4 disks look like one disk, but they are partitioned in such a way that it is either faster or more robust. So that's one type of virtualization. The Andrew file system. This is what we use on the Myth machines. If you ever noticed, if you log into Myth, or you log into Cardinal, or if you log into Myth 52 or 58 or whatever, all the same file system. The reason it's all the same file system is that it's a file system that is spread across all those computers. In fact, Andrew file system is spread across the world. You can go to Carnegie Mellon's. If you can do CD from your Myth to a machine in Carnegie Mellon, now you don't have the permissions probably to do anything, but you can actually CD into it. We always type /user/class. Really, that's actually a link to /AFS/IR/ et cetera. And those are like AFS is the Andrew file system. I think IR is Stanford's or whatever. And so it's mapped to across the world. But that's a virtualization. It looks like there's one file system, but really there's thousands and thousands of computers connected to that one system. They share the file system. Okay. Web server load balancer. This is when you log into Myth, and we did a load balancer in class. We log into Myth, and it comes up with, it sends you to Myth 52 because it's got the fewest number of people on it that are working. Okay. Virtualization is also making one resource look like many. Okay, so what does that mean? Well, this would be like virtual to physical memory mappings. So you know how we've said last time that you have 2 processes and they both think they have all the memory in the entire system. Well, they don't. They only have a little portion of memory, but it's making that one, or it's making the one resource look like many resources instead of the other way around. Okay? Threads. Well, each thread has its own stack segment. Well, that's just a regular stack broken into many pieces. That's virtualization. Virtual machines. So who has used VMware before, right? I think I have VMware on here. Here we go. Here's VMware. I can load, if I load this up, I can load a Linux machine on my Mac that's really Linux, and it really thinks it's talking to hardware directly, and in fact it is, because Intel sets up things to make it virtualization work right. But now I literally have two operating systems running on the computer at once, my Mac operating system and a Linux operating system. And by the way, VMware was the company was started from Professor Mendel Rosenblum, who's here and teaches this class occasionally and some other CS systems classes. He did pretty well creating VMware. But anyway, now I'm just inside my Linux machine up here, and I also can do it. You can do it with Windows or other machines too. I don't even have a Windows PC, but I use Windows programs occasionally, and all I do is run it on VMware, and it makes it easy. So it's a little slower because there's some translation that has to happen, but it's not too bad, and it works pretty well. That's how VMs work. Okay. All right. Concurrency. We've talked a lot about concurrency in this class. Okay, multiple processes, multiple threads, multiple cores on your multiprocessor computer. It wasn't until about 12 years ago you really couldn't buy a multiprocessor computer for less than tens of thousands of dollars. Right? It was really expensive. In about 2006, Intel started pushing out a dual-core machine, which means now you've got a computer that can literally do two programs at the same time, and that's concurrency. Okay, signal interrupt handlers are all about concurrency, right? The signals, your program is chugging along with an interrupt handler. The kernel is doing its own thing, and then signals your handler to stop the rest of your program and handle whatever the child process, a handler, or whatever's happening there. There are languages which are built specifically to do concurrency. There's a language called Erlang, which is a great language, but kind of hard to get your head wrapped around. But it basically doesn't allow race conditions. You can't make a race condition in Erlang because of the way the language is built. Not bad if you're trying to do lots of concurrency. Yeah?
So if signals and interrupts are technically concurrent, how does that work before we get to the processing?
Good question. If signals and interrupt handlers, just like everything else, if signals and interrupt handlers are concurrent, how did it work before multiprocessing? When you have one processor, you can mimic multiprocessing by time slicing everything, right? So the kernel gets a little time, and you get a little time, the kernel gets some time, and you get some time, and your signal handler gets some time, and whatever. So that's how that works. But anyway, Erlang, look it up. It's an interesting language if you want to write very safe concurrent programs. JavaScript did exactly the opposite. They said concurrency is too hard. We're just going to have one thread. Right? And it's not quite as true these days, but it made it very easy to program in JavaScript in some ways, but also not very efficient because it has one thread that does everything. So that's that. Okay? All right. And then finally, we have client-server response, which is a request and response. This is what we've been doing for networking. This is exactly what your MapReduce is doing, where your MapReduce main program is talking to the reducers and the mappers back and forth until it gets all the data back. It's a client-server request. You see this all the time, not just in networking. You see it with multiprocessing. You see it with processors that have to basically talk between each other and coordinate things. That happens. Okay. System calls are also another request and response, right? Where you say a system call and the kernel goes and handles it, you are basically talking to the kernel that talks back to you, that gives you back the answer, and there's that handshake that has to happen via a system call in there. All of the networking protocols, of course, are various examples of client request and response. And then the file systems that we just talked about are also client request, server request and response, because you look for a file, it might not be on the hard drive that the myths are using. It's on the file system that the hard drive's up some other building, which might be, and it might be if you're looking at Carnegie Mellon's, it's on the hard drive over at Carnegie Mellon, and you have to do some requesting, and it's kind of slow in that sense. Okay, so those are the 7 pieces that we covered this quarter. And there's a lot there, but you know some of the details about that. You still don't know some of the abstraction underneath the hood sort of details. You will get those in other classes. But in here, hopefully you can see how many of the things that we've done relate to these ones. What questions do you have at this point? All right. So I will then see you for last class on Wednesday. It is on non-blocking file I/O, and then we have the final exam. No labs this week. We're done with labs. So that's it. We'll see you then.